14.2. In section 14.2, we're going to talk about the regression analysis. In section 14.1, we looked at the general equation for linear equations, and in section 14.2 now, we're actually going to use those linear equations in this section. So, in chapter 14, we're getting into the prediction portion of the course. So the idea is to predict the value of one variable from that of another variable. Okay, so for example, let's say if you know a person's height, you could possibly predict their weight. If you know their incoming GPA, you will be able to possibly predict the test score. Or for example, if you look at the age of a person, you can predict their cholesterol. So things that are in that nature. As far as the coverage goes, we're going to cover all 4 sections of chapter 14. Again, 14.1 we've already covered. In this section, we're looking at section 14.2. So this is the focus of our discussion in this lecture right there, the linear equations. Okay, so and also I want to point out that in this section, and in fact in all of chapter 14, we're not going to do anything by hand. So you do the entire chapter using StatCrunch or any other software you can use. So here I have listed the things that are on our agenda here. So first, let's begin with what is the objective. Once again, our objective is to predict the value of one variable from that of another variable. So in that case, this suggests that we have two random variables, that is. And because we have two variables, we call these bivariate data. Now here, we're going to reference these two variables as x and y. And x here is going to be the independent variable, and y is going to be our dependent variable. Okay. Now, for our discussions in this course, we assume both of these variables are quantitative variables. But strictly speaking, it is possible to actually have qualitative variables in regression, but we don't address those in this course. Now, here is some terminology for dependent variables. Independent variable is also known as explanatory, predictor, or regressor. Dependent variable, on the other hand, is called these other terminologies. We often refer to those as a response variable or predicted variables. And they're also called regressed. So for those that, let's say, call x, remember independent is x and dependent variable is y. For those who call x regressor, those folks call y regressed. So that's the idea. For those who call x predictor, those people call x predicted, and likewise those who call x explanatory typically call y the response variable. Okay, just the terminology. Now, here is the gentleman that actually discovered or developed the whole idea of regression analysis, Sir Francis Galton. You can do a Google search on him, and you can see that he's a polymath. He was really good at what he was doing, and he was into a lot of different various fields of endeavor. So he wasn't just in mathematics. And he is actually the person who coined the term regression. Sometimes he called it regression to the mean. Sometimes he called it reversion to the mean. And nevertheless, the idea of regression is to fit a line through a set of scores. Okay, and then use the line to predict the value of response variable. So again, you can read more about him and the data that he used. If I recall correctly, when he was doing regression, he was interested in looking at the relationship between the heights of fathers and their offsprings, their sons. his premise was that taller fathers tend to have taller sons and shorter fathers shorter sons. And alongside his research, he found out that beyond a certain point, the height, the taller the father was or the shorter the father was in both extremes, that the height of the son was not necessarily as tall as or as short as the father, and that the height of the sons tend to regress, means go back to, regress toward the mean of the data set. And then he coined the phrase regression to mediocrity, reversion to the mean, or regression to the mean of the data of dependent variable. So again, you can read about it, and it's a very interesting story. Now here I have what we call a scatter plot. So let me just put the phrase here. This is what we call a scatter plot. A scatter plot is just that. So for example, there you go. This would be my x and here's my y. Okay, and it's a two-dimensional plot of all the data points. Okay, so for example, if I look at the point here, this individual point here, right in here, this has an x and a y component. Okay, so that's what that is. Now, if I was to fit a line through these data points, okay, sorry about this. This thing keeps popping up. It'll go away. Okay, so suppose I want to fit a line through these data points. Okay, and I'm going to draw several lines, and you kind of try to visually follow what I'm doing here and tell me what you think. Well, don't tell me, but in your mind, think about if these lines are, which line is actually a better line of fit is my point. So there we go. This is my prediction line. So if I want to predict these scatter plots, right, the data points, if I use the green dot, well, at the given value of x, this would be the predicted value of y, right? Now, if you actually delve into the data, this is where the data points are. So the line is actually not even close to any of those data points. In fact, it's not close to any data point in that two-dimensional plot. So I guess we have maybe a consensus here that this is not the best line of fit, right? This is not a good line. So we're gonna remove this line. Okay, now let's take a look at another line I'm gonna draw here. How about this line? Is that a good line for prediction? Again, by same token, because for any given value of x, if I predict, my predictions are all going to be here. And looks like this line too, just like my green line, it's going to miss all the key data points, right? None of the data points, in fact, will be even close to these lines. So neither of these two lines are good lines of fit. Okay, so we're going to remove this one. Now think about this one. How about this one? This one goes through some of them, right? Look at this one. Look at this one. Well, at least some of these, well, maybe this one is getting better. This one, I'm not sure. It's not getting close to a whole lot of data points. But you get the idea of where I'm going with this, right? The idea is to draw a line that gets as close as possible to all data points and go through as many points to where the points kind of scatter about it. So there you go. Let's say this is my, I know it's a thick line, but there you go. For example, that would be a good line, except my line is too thick, right? So let me actually draw a thinner line. That's much better, right? So that's probably the best line that I have drawn throughout this process. So that's going to be our, I guess, the common sense, the common sense logic, I guess, of how we would actually go about doing this. So now for us, the line of best fit is going to be the one that gets as close as possible to all data points, right? You can remember, this line is no good, this line is no good, that's no good. The one that I have here, this is the one of, it looks like the best line of fit, right? So that's what we want to do. We're interested in the equation of this line, by the way, the mathematical equation for this line of best fit. So now getting into the mathematics of it. So the best line of fit is the one that actually going to, in terms of mathematics, is one that minimizes the vertical distances from the line. Okay, and I'll show you in a moment what do we mean by that. From the line to the observed value. The line here, by the way, we're talking about this line. We're talking about the regression line here. Okay. Now, this is a sketch that I have drawn. So hopefully this will clarify what we mean by vertical distances. So if you look at the line here, okay, so this line is actually, sorry about that, this line is actually my regression line. And this is the actual y value, an observed value, a single data point. This is my regression line, and this is what we call the predicted value because it's on the regression line. So we use the hat notation, by the way, the caret sign for predicted value y. And I have subscript I here because this is for the ith observation. So I could have, I don't know, 8 data points, right? So I could have x sub 1, x sub 2, sub 3, sub 4, sub 5, and so on. So this is y sub I, the actual y value. Okay, and that's what that is. And this is your y. Now, the difference between the actual and predicted value is what we call the error or the residual, right? Clearly, the actual value is higher than where the green boxes, right? The predicted value is. So there is a discrepancy, if you will, between the actual and the predicted value of y given by the regression. That discrepancy, the deviation, it's called the residual or the error. So the line of best fit is the one that minimizes those vertical distances. Now, the actual criterion that is used here, it's called the least squares criterion. That's the criterion that is used in fitting the line of best fit, okay, through these data points. So what is the least squares criterion? The least square criterion tells us that the line that best fits the point having the smallest possible sum of squared errors. Okay, so again, the line that best fits the points having the smallest possible sum of squared errors. That's what the least squares criterion says. Now, one thing here, by the way, is that we're looking at squared errors. And the reason we look at the squared error is this. Let me do this on the side. Let's say I have some data points here, 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 and here, like that. There you go. So each of these have their own vertical distance, right? There is an error for every one of these. So this would be like E1, error second, E3, E4, E5, E6, and so on, right? Now, just by nature, the mathematics of it, which I won't show you, but it's true, folks, trust me. By sheer mathematics, if you look at the sum of sigma of EIs for all i's, some of those deviations about the regression line turns out to be 0. Okay, so for that reason, instead of summing the deviation and getting 0, we actually look at sum of squared deviation. This is the reason we look at the squared errors. Okay, now let me go back here. So now the regression model that we're working in this course is called a simple linear or first order model. This is the simplest of all regression models that we're going to look at. The regression model is a serious topic in statistics, and it's very, very vast. So we're just going to kind of scratch the surface a little bit here. So we're going to look at the simplest linear model just to get you familiarized with the idea of prediction. It's called simple because there's only one independent variable, 1x. That's why it's simple. And it's linear because our model is a straight line model, so that's why it's called linear. The first order model here, they call it, as I have in here. Again, this is first order. First order means you only have x to the first power. First order. The order is the exponent on x here. Okay. Now, here's what your book tells you about the regression line. The regression line is a line that's best fits a set of data points according to the least squares criterion. And what is a regression equation? It's the actual equation of that line. So the regression equation, therefore, this regression equation is actually, this is the one that they're referencing. It's the equation of regression line. Okay. And let's see the next idea here. Oh, the notations. Now, I'm showing you this just for completeness, okay, to be complete. But we're not going to, as I promised, we're not going to do this by hand. We're going to use the StatCrunch to do this. But I just want to show you how this goes. It does involve a lot of sigmas or summation notations here. This is actually the equation, the regression equation. Notice again B1 here and B0. This B0 is the y-intercept. And B1 is the slope of the line. Okay. And here are the formulas. That's for B1, and this is a formula for B sub 0, which you don't need to bother with because, again, we use software to do this. Now, a few things before we actually go through an example, and I'll show you how to do this in StatCrunch. In this section, they talk about extrapolation. When you extrapolate, means you go beyond the limits of your data. Okay, in this case, more specifically, you go beyond the domain of the equation. Okay, so what are we talking about here? We're talking about a variable x. Okay, the domain of this variable is the minimum of the data, which is here. That means the value of x is maybe 2. And the maximum is 7. So let's say I'm going to go to about here. Okay, theoretically, it actually ends at 7, right? So this is going to be 7. In other words, the domain of this equation is between 2 and 7. Now, whatever this data is, it doesn't matter. But this data, actually, it's an example in the book. And the author is looking at, the data is looking at the price of some automobiles. So Y here is the price in hundreds. So a number like 120 means $12,000. And X is the age of the automobile. So 4, X is 4, means 4 years. And there you have it. Now, so the scope of our independent variable, again, I'm going to write this X between 2 and 7. That means, what does that mean? This means that if I want to use the prediction line, let me clean this up. If I want to use the prediction line to make predictions using this equation, the equation of this line, I'm only supposed to use it for x's between 2 and 7. That means automobiles between 2 and 7 years. Because this one, again, this example of the price of automobiles, I guess more specifically, they're looking at price of Orions. Whoever makes Orion. So again, that's what the domain is. Now, what do we mean by extrapolation? So extrapolation means you go beyond these limits. So you can actually exceed it in this direction, right? So you're extrapolating here, and you can extrapolate here beyond your minimum and maximum x value. So the author actually warns us against extrapolation. So you got to be careful when you do regression analysis that we do not extrapolate. Make a long story short. Okay. So remember, we cannot do not extrapolate. Okay, so, and here you can see kind of a danger of in extrapolation. For example, if I use the regression equation here to predict the price when x is 0, well, x0 means 0 age on a car means a brand new car. Well, that means the y-intercept. The y-intercept here is going to be about, I don't know, maybe 20,000, 21,000, something like that, 20K. Well, a brand new Orion may not be $20,000. You go to a dealer, it's maybe about 19,000 brand new. So it doesn't make sense in this case to extrapolate to to below 2 years of age. Okay. And on the other side, actually, too, if we look at the other extreme here, for example, let's take a look at a car that is 10 years old. A car that is 10 years old using the regression line, almost 10 years old, that's going to be, what, 0. That means it has no value. And in fact, if a car is 12 years old, look at this. For a 12-year-old car, it runs about -50, $5,000. That means if your Orion is 12 years old, you got to pay someone $5,000 to take your car from you. So you kind of see, again, all of these examples lead to the conclusion that extrapolation is not allowed in regression. Okay, so we can't do that. Interpolation is fine. It means from, in this example, again, from 2 to 7, we can interpolate and get the price of the Orion. And what we were predicting, by the way, here, y hat here, let me write this here for you. I know y hat is the predicted value. That's what the very generic term, predicted value, that's what it's called. But more specifically, what we're predicting is really the average y value is what's being predicted. We are predicting the average y value for a given value of x at a given level of x. Okay, so it's important to note again that we are predicting the average. So in this case, for example, if I use a regression line to predict the price of a car, I'm predicting the average price of a car, Orion, for whatever age I'm looking at. The next idea we're going to look at is called influential observations. Okay. Now, in this example, again, this is the example for automobiles. With influential observation, and you can kind of see that the author has written it, I've highlighted it myself. This observation is called influential. Now, why is it called influential? Because if you look at this packed group of data points, this one is like an island unto itself, right? It's kind of up there alone, away from the rest of the group. So that's why it's labeled or flagged as influential observation. Now, there's one way you can actually identify influential observation. Let me write that for you. This is important. Influential observations lie alongside the regression equation. Okay. They usually go in tandem with it. So, for example, let me draw another influential observation made up. This, for example, this one, I'm down here. This is going to be another influential observation. You see how it's near the line, right? Again, I'm looking at this one. It's near the line, and it's away from the rest of the group. You can have more than one influential observations. So I could have, let's say, one up here. That's almost a brand new Orion, a brand new car. So these influential observations, again, are away from the bunch, the majority of data points, and they are alongside, they go right along the regression line. Now, what do they exactly influence? What they influence is the regression slope of the regression equation. So in this example, what the author has done is this. The blue line is the regression line, including that influential observation. And then the second line is after he removed that influential data point. And notice how markedly that slope changed. Look at that. You see that? The slope, it actually changed quite a bit. And that's why they're called influential. So influential observations, they influence, quote unquote. What do they influence? They influence the slope, okay, of the regression line. That's why they're called, again, influential observations. Okay. Now, the other idea here is outliers. I didn't have a scatter plot in the exercises for outliers, so I just made up my own here. Okay. Now, here's an example of a scatter plot of just made up data. Okay, so here's again my x, and here's your y value. Independent, dependent. Now, notice this time these two highlighted points that I'm looking at. I'm looking at this point and this point. These points, they do not lie alongside. Alongside means this, means right like that. See, these are alongside. True? Those green dots are alongside of it. It goes along the line. Well, the one that I have up there, those do not run alongside. These are actually away from the regression line, aren't they? Look at this one. You see that? It sits directly above the regression line. And for that level of x, whatever this level of x is, you would expect these points to kind of, what the data suggests is that you have points that are on or about there within this much range, right? From here to here, that would be the range of y values for this given x value. But look at this one. It actually sits away from the rest of the group. Okay, so outliers, these are the points that fall away from the regression line. Okay, and that's what those are. So we're going to, again, call those outliers. And again, you can have more than one outlier in a data set. True? In this case, I have two. And there you go. At this level of x, notice your data bunches around here. So this would be an outlier, the one that falls way below the line relative to the rest of them. Okay, and the next idea is actually working an example. So we're going to use the StatCrunch, in fact, for regression and correlation. So here's an exercise. Okay, and I think I've talked about all of these items, A through G almost. Well, G is a prediction, right? In part G, we're making a prediction. So we'll see how that line is used, what it's good for. So let's actually go through parts A, B, C through G. In part A, the question says find the regression equation for the data points. In part B, okay, so that's part A. In part B, graph the regression equation. Both of these we get from StatCrunch. Okay, describe the relationship. We'll do that. Interpret the slope. We always interpret the slope in context in a regression problem. So we have to do that, not StatCrunch. Identify predictor and response variable. We will do that. Identify outliers and potential influential observations. So we've talked about all of those terminologies. And finally, in part G, we're going to use the regression line to make our prediction. That's what it's good for, to make those predictions. So first I'm going to show you the answer to the exercise, then we'll go to StatCrunch and do this together and we'll be done. So here is the actual exercise that's in the book. In exercise number 52, it reads, Hannah Properties specializes in custom home resales in the Equestrian Estates, an exclusive subdivision in Phoenix, Arizona. A random sample of 9 custom homes, so that's your sample size, right? N is 9. 9 custom homes currently listed for sale provided the following information on size and price. Here X denotes the size in hundreds of square feet, and Y is the price in thousands, right? So remember, this is in thousands and X is in 100 square feet. So the way I understand it is the 22 number here. 22 means 2200 square feet, and that sells for $496,000. That's how you work the 3 zeros. Okay, so that's just to understand the data that we're given. Now, let's take a look at the regression. There you go. Pretty simple, petite. Now, I actually took a little cutoff of the regression output. I'll show you the full-blown output in a minute. I just took the part, cut and paste the part that I needed for this exercise. And notice, by the way StatCrunch labels the regression equation, it doesn't use B0, B1, Y hat. It actually uses descriptive words for X and Y. You see that? Wasn't size X and price is Y. There you go. So a lot of almost exclusively all statistical packages do that. They actually have descriptive verbiage for the variables, which makes it useful. So you don't have to go back and say, okay, well, what was X? What was X1, X2, X3, so on and so forth. Okay. And of course, we talk about the correlation and all of that stuff. This, we save it for later on, this part. You can just kind of ignore it for now, okay? So don't worry about it for now. And let's take a look at, so there you go. That's the answer to part A. Now, if I put it in a familiar format, by the way, Y hat equal B0 plus B1X that we talked about. So that means the predicted value of Y is 140 plus B1 is 15.9. I'm rounding these numbers, folks. So my equation looks nice and clean. If you want more decimals, they're all here. You see that? All those decimals, you can see them. Okay, so there's our regression equation. That was part A. In part B, it reads, graph the regression equation. I'm up here. Graph the regression equation and data points. Okay, and again, StatCrunch did it right in here. So you can kind of see the apparent relationship seems to be linear, sort of, kind of, but you know, it would be nice if it looked like this, right? But it didn't. And with the real data, that seldom does, if ever happens. If this happens, by the way, every single point would be exactly, precisely on the regression line. The model becomes what we call a deterministic model, means it is error-free. Right now, our models are probabilistic models, means there is a probability of missing a point and have error in predictions. Sorry about this. Again, this pops up. Okay. And let's take a look at now. So this answers part B, right? Here's the graph of the scatter plot. So with the scatter plots, again, you get these individual dots, right? They're scattered. You see them? These are scattered points. And then your line of fit, your regression line, is the one that's fit through the data points. That answers part B. In part C, describe the relationship. Well, looks like what, a linear relationship. And that's what it is. Part C is linear relationship. In part D, the question read, interpret the slope Part E, identify predictor and response. Well, let's see, interpret the slope. Okay, so remember the slope of this line is right here, right? That's the slope of the line. Now, I'm going through some actually detailed work on the slope. It helps me, it will help us to interpret the slope. Remember, the more general form of a slope is the change in y over change in x, right? In this particular exercise, y is the price and x is the size of the house, right? And the number that was from the output was 15.89. And that 15.89, I can write it as 15.89 over 1. Any number that output gives us, write it over 1. Always divided by 1. Okay? Now the numerator is in thousands of dollars, denominator is in 100 square feet. True? So what I did next is I actually moved those zeros in front of the numbers. 15.89 means 15,890. Just simple, you multiply 15.89 times 1,000. Okay, you get 15,890. That's how I got the numerator. And 1 in the denominator, remember units are in 100 square feet. 1 means 100 square feet. So now I actually have something that's more familiar to us. See? Dollar per square feet. So that's actually good information, huh? So looks like the slope of the regression regression equation in this exercise actually gives us the price per square footage of these homes in Phoenix, Arizona, in that particular estate, in that location. So if I want to buy a house there, for example, I can imagine paying about $160 per square feet on average to purchase a home in that location. So again, slope we always interpret. Now, part E said identify predictor and response. Remember, predictor is X, response is Y. And actually right in here, we know what those are. X is size, Y is price. True? So I went ahead and wrote that. X is size, Y is price. So our predictor is size, therefore. That's what our predictor is. Our predictor is size and our response is price. Okay. Done with that exercise. In part F, I believe that's the part for influential. Yeah. In part F, the question asks, identify outliers and potential influential observations. Okay, that's what we want to do. Outliers, potential. Remember, outliers are away from the trend line, and influential observations lie alongside of the trend line, the regression line. And what I have done is, right in here, I kind of copy and paste the scatter plot down here for us to take a look, because this is a visual thing for us. So now remember, the only point that I see alongside is this point, right? It's this point that lies alongside. See, there's a regression line and it lies alongside of it. Any point like this would be influential. That one would be influential. And also there's actually influential on the other extreme. Check this guy out. You see this one down below near 0? It's influential because it's away from the rest of the group, and it lies alongside of the regression line. So we have two potentially influential observation, and this one as well. Let me just, there you go, circle this guy and call this also influential. Okay, so we got a couple of influential observations. Now, these 2 points, I have them as potential outliers. Okay, that's this point, this one, and this one. And the reason, again, they're potential outliers because look how far the vertical distance is from there. You see that? So now we have actually quantitative procedures. There's actually hypothesis tests that we can do that they formally determine whether a point is an outlier, if a y value is an outlier. So there you have it. Also for influentials, we have procedures, but we don't look at those in this course. So there you go. So we have two potential outliers. And in part G, now we want to make a prediction. Clearly, this is the prediction that they got from StatCrunch, right? This is the prediction from StatCrunch. But if I want to do it by hand, it's really not that bad. So you go to your regression equation, and where it says x in here, you plug in the number. Now, the problem, actually, in the statement of the problem, notice it says 2,600 square feet home. It doesn't say 26. But because the units on X are in 100 square feet, when you actually plug into your equation, you got to plug in at 26. Okay? Do not put. Let me just say this one. This is not 2,600 in here. Don't type 2,600. If you do, put two more zeros in front of it. That's a house that is 260,000 square feet. If you put 2,600 into your regression equation. And you can see that in here also. You see that I put 26 in StatCrunch. I didn't put 2,600. So I plug it in, do the arithmetic, use a calculator, and you get 553.3, and that's what the predicted value is. And what is this value? This is actually $553,300. Remember, you put 3 zeros in front of that, and that's what that is. So you would expect to pay, and this is, let me emphasize, this is the average selling price. Average selling price, that's what that is. Okay. And the reason it's average because let's say there may be 5 homes that are each 2,600 square feet. So it gives you the average of those homes. Okay. So in general, we predict the average price. Even if there weren't there, that means if there were other homes of that size, they would average to this price. Okay. And one more thing, and then I go to StatCrunch before I forget this part. Here, he's trying to give us a warning as far as the use of linear regression is. The key word in linear regression is the word linear. You see that? That means a straight line. So our assumption is that, as he has mentioned here, that the points are scattered about the line, right in here. That's our assumption. That means this is our assumption. Okay, there you go. So if you have a data that bends, it wouldn't make sense to fit a line through the data points, right? So that's what he's referring to here. If data does not exhibit a linear trend, we should not even do regression. So we just stop. It's like, well, can you do something for me? Of course. And usually we stop with linear regression. Now look at this data. Let's say if I had the know-how, if I can fit a curve through this, this is going to be perfect fit, wouldn't it? In fact, it looks like this. There's going to be a parabolic possibly, right? Look at that parabola. This would be some kind of a parabolic ax squared plus bx plus c model. There you go. That's my y hat. So the idea again is away from linear regression. Remember, your linear is y hat b0 plus b1. So that would be a different fit. Now, again, we don't cover anything that sophisticated, but the point being that if you draw the scatter plot and the data does not exhibit a linear tendency in the data, then we should not use linear regression. Now, let me actually go to StatCrunch and do this exercise together. This is exercise number 52, and then we'll be done with this lecture. So in exercise number 52, let me hopefully, and there you go. So I already have StatCrunch running. And in exercise number 52, I'm going to click on chapter 14 here. Okay, right here, chapter 14. And scroll down to number 52, and this will actually import exercise number 52. There you go. And you can see in this exercise here, first column is size, then that's the price of these homes. And here's how easy it is, folks, to get that regression output. You go to stat, down, 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 down to regression. See, it's very, very self-explanatory. And what we're doing is simple linear. That's all we're doing in this course. Simple linear. And look at what little we have to do here. All it's asking for is, okay, well, where is your x variable? Remember, x is independent variable. That was size. Dependent variable y is price. Now, if I, for example, by mistake, let's say I put price here and I put size here, that wouldn't make sense, because that means we want to predict the price of we want to predict with this option, which is incorrect. I want to predict y variable. So that means I want to predict the size of a house from the price of a house, and that's misleading. Like, for example, if I told you a house is selling for $450,000, it's hard to, it wouldn't make sense to determine the size of that house, right, from its price, because the price depends on location, of course. So anyway, I just want to say that it wouldn't make sense to do that. But it does make sense. The price is actually influenced by the size of a house. Typically, bigger homes in that same zip code, in that same, let's say, cul-de-sac, homes that are bigger cost more, right? The price is higher. Don't worry about anything down here. Now, if you want to get StatCrunch to make a prediction for you like I did, if you go down here, it says X values, prediction of Y optional. I'm going to type 26. You see that? If you want, you can actually type, I don't know, 30, comma 30. So I want two predictions with this one. The book only asks for one. I'm just going to show you. You can get multiple predictions. Compute. There's the regression output. And here is the part that I actually cut out. It was this portion right in here. So here's the equation that I got, the regression equation. Don't worry about this portion, although you can kind of see intercept 140, that's this number. Slope 1589, that's that number. And this is actually chapter 15 deals with hypothesis test. We can test hypothesis about the slope of a line. Is the slope 0 or is it different from 0? Remember, slope 0 means flat line, means there is no trend in the data. So that's what this is. You can ignore this portion. The analysis of variance we'll look at actually in the next section. So, but for now you can ignore this also. And here's my predictions. You see that? I put 26, and this is the predicted price, 553,000. You want to know what the 3,000 square feet home in that location is? It's about $617,000. And of course, these are self-explanatory. This is chapter 15. We don't cover these items. Okay, but in this section, this is all we want, is just the predictions. All right. Now, if you go down to the right, you see the arrow here I have and the yellow highlight. If you click on that right arrow, you actually get the regression line and the scatter plot. If you actually hold over the point and let go of the mouse, it shows you the data is in row 7 of the table and the price. Oh, there you go. This is the actual price. This size is 30, means 3,000 square feet. The actual price was 738,000. This is cool. I just randomly put 30. So that 600 and change was this number right down here. You see that? And if you hold, by the way, the mouse over the line, it shows you the regression equation. Okay. Look at this one. This one is a house that is 2,200 square feet. That's the smallest house in that estate, and it sells for about $500,000. Okay, so that's how you get these, and there you have it. So hopefully, again, you saw how easy, simple it was to get the regression output from StatCrunch. And I believe that's all we wanted to do, correct? So, as always, again, if you need more review, please go back to the beginning, and you can pause the video, kind of digest what you read, and you can also kind of scroll this, right? You can kind of look at things a little bit at a time as the video plays. You can pause it, again, read, digest, whatever helps you learn the material your way. But we're done with this lecture for now. So our next section would be section 14.3, and in section 14.3 we're going to talk about coefficient of determination. One thing before I leave is that the question might be, well, so I have a regression equation, right? Well, how good is this model for prediction? Does it have any predictability power? How powerful is this model? So in section 14.3, we actually look at how we can assess the strength of the linear regression model, the strength or the adequacy of our predictions. Okay, so on that, we are done with this video.